All of the SN2 reactions that we've dealt with so far have involved negative nucleophiles. In this video, we will discuss how to handle SN2 reactions that involve neutral nucleophiles. So first of all, let's review what is the definition of the term nucleophile. As usual, I hope that you're pausing the video to answer each question that I pose, and I hope you said, here's the definition of a nucleophile. I hope you gave a two-part definition. A nucleophile donates electrons to join an electrophile. Next question, how would you draw the electron pushing arrow for a nucleophile? Here's the answer. The nucleophile is the electron donor, so it should go at the tail of an electron pushing arrow to show the electrons moving away from the nucleophile. The nucleophile is going to join an electrophile, so at the head of this electron pushing arrow we place the electrophile. Next question, what is the clue that we've learned for identifying a nucleophile? Answer. We've seen that an atom with a negative formal charge is likely to be a nucleophile, because if something's negative, it would like to get rid of that negative charge by donating negative electrons. What do we do when none of the atoms in the starting materials have a negative formal charge? If there's no atoms in the starting materials that have a negative formal charge, what's another clue that we can use for a nucleophile? What would be a clue for a neutral nucleophile? You actually probably have already seen this clue. So have you seen in your class what's a clue that a neutral atom could be a nucleophile? Well, a neutral atom can be a nucleophile if it has a lone pair. And that should make sense to you. Electrons in a lone pair are less stable than electrons in a bond. So if there's electrons in a lone pair, they would like to be donated so they can move from the lone pair to a bond. So it should make sense that an atom with a lone pair would like to donate those electrons. Now, how can you tell whether a neutral atom has a lone pair? Well, you should just memorize that usually when we're talking about a neutral nucleophile, we're usually talking about one of these four atoms. So you should just memorize that neutral oxygen, neutral nitrogen, neutral sulfur, and neutral phosphorus all have lone pairs. Here are nitrogen, oxygen, phosphorus, and sulfur in our periodic table. You should just memorize that each of these elements has a lone pair when it's neutral, so each of these can be a neutral nucleophile. These four elements are the neutral nucleophiles that you're likely to see used in your Ochem class. Unfortunately, almost every rule in organic chemistry has an exception. There is an exception to this rule. There are some neutral atoms with lone pairs that are not usually used as nucleophiles. Neutral chlorine, neutral bromine, and neutral iodine all have lone pairs, but nevertheless, they're usually not used as nucleophiles. That shouldn't surprise us so much because we have a different role for these elements. What role would we use a neutral chlorine, bromine, or iodide for? You should know that neutral chlorine, bromine, and iodide are very often used as leaving groups. So if you know that these are used as leaving groups, we would not expect them to be nucleophiles. Here are chlorine, bromine, and iodide in the periodic table. Now remember that the most important factor in organic chemistry is formal charges. The formal charge makes all the difference. A neutral chlorine, bromine, and iodide are not nucleophilic, even though they have lone pairs. On the other hand, we've seen many examples that a negative chlorine, negative bromine, or negative iodide definitely are nucleophilic. So you can't just say that bromine is a nucleophile or that bromine is not a nucleophile. You have to specify the formal charge. Neutral bromine is not nucleophilic, even though it has a lone pair. Negative bromine is nucleophilic. The upshot is that you should memorize that neutral oxygen, neutral nitrogen, neutral sulfur, and neutral phosphorus are often used as nucleophiles because they have lone pairs. pause the video and see if you can find each of these elements in this table. Well, here's neutral oxygen, and here are neutral nitrogen, phosphorus, and sulfur. So you can see that there's an important difference between these elements. Neutral oxygen is nucleophilic, but it's a poor nucleophile. Neutral oxygen is a poor nucleophile. It's good enough for SN1, but you can see that neutral oxygen is not good enough for SN2. So we will not be using the oxygen, we will not be using neutral oxygen as a nucleophile for SN2. Again, the most important factor is the formal charge. We've already seen that a negative oxygen is a good nucleophile, and it is good enough for SN2. But a neutral oxygen is a poor nucleophile, good enough for SN1, but not good enough for SN2. On the other hand, you can find neutral nitrogen, neutral phosphorus, and neutral sulfur here in the middle column. So these are good nucleophiles, good enough for SN2. So in summary, you should have memorized that neutral oxygen, neutral nitrogen, neutral sulfur, and neutral phosphorus can all be used as nucleophiles because they have lone pairs. Neutral oxygen is a poor nucleophile in the left-hand column of this table. Neutral nitrogen, phosphorus, and sulfur are good nucleophiles in the middle column. Summarized here on the screen is a summary of the key information that we've learned about these key roles in organic chemistry. And here circled in red is the key new information that we've learned in this video about neutral nucleophiles. To succeed in organic chemistry, you need to have complete mastery of all the ideas in this summary. So now would be a good time to pause the video and make sure that you have complete memorization and mastery of all the ideas on the screen right now. It would be good to try to take a blank piece of paper and try to write down all of these ideas from memory. To succeed in organic chemistry, you must have complete mastery of the ideas in this summary. As you continue studying organic chemistry, you will be adding additional information to the material that we have here. This is just a starting point for learning about roles in Ochem. Please pause the video and try this problem. Now let's discuss. I'll start by numbering all the carbons. Now the next step would be to look for ionic bonds. That would involve metals. Notice that there are no metals in these starting materials. In particular, there's no sodium or potassium. There's no metals, and therefore there are no ionic bonds. All the bonds are covalent, so we can assume that there are no formal charges, since none have been drawn for us. So we can assume 0 formal charges here and 0 formal charges here. This is completely covalently bonded. Remember that hydrogen is a nonmetal similar to carbon in electronegativity, and nitrogen is a nonmetal, so this is a nonmetal covalent bond, no formal charges. All right, so now we want to identify the roles that atoms would play. Now, normally we would try to use formal charges to predict the roles, but here there are no formal charges, so how are we going to identify, say, the nucleophile? Well, now we've learned that we can use a neutral atom as a nucleophile if it has a lone pair. And we've specifically memorized that neutral nitrogen is commonly used as a nucleophile because it does have a lone pair. So I will identify the nitrogen as the nucleophile. Don't just say that the NH3 is the nucleophile. Try to identify the specific atoms that will play each role. What about this neutral bromine? Neutral bromine also has a lone pair. So could the neutral bromine be a nucleophile? Well, probably not. Remember that we just learned that even though a neutral bromine has a lone pair, it's usually not a nucleophile. Instead, neutral nitrogen is one of the elements that's oftentimes a nucleophile. Now that shouldn't surprise us because we know separately that neutral bromine likes to be a leaving group. So I would expect the neutral bromine here to be a leaving group. Because it's attached to the bromine, carbon 4 will have a delta positive charge, which will make it a good candidate for the electrophile. Because it's attached to the leaving group, carbon 4 is also called the alpha carbon. Now we have to determine what mechanism we're using. Don't assume it's an SN2. Let's figure out if it's SN2. Well, carbon 4 is a primary alpha carbon because carbon 4 is attached to one other carbon chain. So we expect to use the top row of the table for primary alpha carbons. Our nucleophile is the neutral nitrogen. Well, here is neutral nitrogen in the middle column of our table. Middle column, top row, the table predicts an SN2 reaction. Make sure you write down the name of the mechanism. Now, how do we draw the electron-pushing arrows? Well, what happens in an SN2 reaction? How many steps? How many steps are there in an SN2 reaction? One step. And what should happen in that one step? You should have memorized that what happens in the one step is that the nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. Let's draw the arrows for that. So to show the nucleophile joining the alpha carbon, the arrow should go from the nucleophile towards the alpha carbon. Remember, a nucleophile is an electron donor. So it goes at the beginning, at the tail of the electron pushing arrow. Don't draw the arrow like this. Some professors would consider it wrong to put the tail of the arrow directly on an atom. Instead, it's best to put the tail of the atom on a lone pair. That's the same pattern we've been following with our negative nucleophiles. And we need another arrow to show the leaving group leaving the alpha carbon. Do these electron-pushing arrows that we've drawn make sense? Well, remember, our most important tool for getting the electron-pushing arrows correct is the formal charges. So let's check whether these arrows are consistent with our formal charges. Well, we've seen that we would usually prefer to put a negative formal charge at the beginning of a string of arrows. However, in these starting materials, there were no negative formal charges. Well, in that case, we know that it is also okay sometimes to put a neutral atom at the beginning of the arrows. And that's what we did here. We put a neutral atom at the beginning of the string of arrows. In fact, since there were no formal charges anywhere in the starting materials, we had to put neutral atoms at the beginning, middle, and end of the string of arrows. But you can see that is consistent with what we said before. We said earlier that it is okay to have a neutral atom at the beginning, middle, and end of a series of arrows. When possible, it would be nice to put a negative charge at the beginning and a positive charge at the end of this series of arrows, but that's not always possible. This is a case where we can't do better than using neutral atoms at the beginning, middle, and end of the series of arrows. Now we can draw the products. Now, here are some actions that we should take whenever we're drawing the products of a mechanism step based on the electron-pushing arrows. As we've seen, we should always number all the carbons in both the starting materials and the products. I've gone ahead and done that. Oh, was I consistent about that? Let's see. For some reason I numbered this carbon as carbon 6. I could call this 6, but I guess it would make more sense to call this carbon 5. And then this would be carbon 5. All right, I guess those would be better numbers. Make sure your numbers are consistent in your two pictures. Now, for every electron-pushing arrow, we should be either erasing a bond or drawing a bond or both. So what do you think this arrow tells us to do? Well, I hope it's clear that this arrow tells us to draw a bond. Between which two atoms? Between the nitrogen and carbon 4. I think that should be very intuitive that that's an arrow that tells us to draw a bond between this nitrogen and carbon 4. Now, should this nitrogen still be bonded to these three hydrogens? Well, yes. Remember, we only break a covalent bond if there's an electron-pushing arrow that tells us to break it. There's no electron-pushing arrow telling us to break the bond between the nitrogen and the hydrogens. The tail of this arrow is not on the bond, it's on the lone pair. So this would definitely be wrong unless we pull along the hydrogens. The hydrogens are still bonded to this nitrogen. They're covalently bonded, not ionically bonded. Now, something else we have to do is change charges. As we've discussed, we should make the atom that loses electrons from the first arrow one step less negative. Well, this is the first arrow. This is the first arrow in the series, so we should make the atom that's losing electrons from this first arrow one step less negative. because it's losing electrons. So what will be the new charge on this nitrogen? Well, if this nitrogen is already neutral and it becomes one step less negative, isn't that the same as one step more positive? So the nitrogen should end up with a positive formal charge. The nitrogen started neutral and it lost a negative electrons. So it becomes one step less negative. One step less negative is the same as one step more positive. So it goes from neutral to positive. It should make sense that if you lose electrons, a negative charge, you can go from neutral to positive. When we're drawing this product, what's the most important part of the product to get right? The formal charge. So what's the most important part of this product to get right? The positive formal charge on this nitrogen. What's the most common mistake that students make on this problem? They forget the positive charge on the nitrogen. You would lose a lot of credit if you forgot this positive charge because it's the most important part of this product. Now we can deal with the second arrow. Does this arrow tell us to draw a bond, erase a bond, or both? Well, I think it should be intuitive that this arrow tells us to erase a bond between carbon-4 and the bromine. And in fact, I've really already erased the bond between carbon-4 and the bromine. And because this is the last arrow in the series, it also tells us to change a charge. This bromine started neutral, and it's gaining electrons, so it should become one step more negative. So we need to put that negative charge on the bromine. Now this question is asking us to draw the product, so you might think that the best way to draw the product is like this, since this is probably the product that the professor cares about. But when your main product has a formal charge, there's a different way that's conventional to draw the answer. Since our main product has a positive charge, the conventional way to draw the answer here is to draw this product ionically bonded to the Br-. So the conventional way to write this answer would be to draw, how do you show that this product is ionically bonded to the Br-? Well, remember you can show an ionic bond just by drawing two things close to each other. So we can show that these are ionically bonded by drawing the negative bromine close to the positive nitrogen. Here's the conventional way to draw the answer to this problem. When your main product has a formal charge, it's conventional to show it ionically bonded to the other product. And you show the ionic bond just by showing these two products written close to each other. So notice I'm not including a plus sign. I'm not including a plus sign because we're thinking of this as a single ionic compound rather as two separate products. That's the conventional way to draw the answer when your main product has a formal charge. We haven't had to draw any of our previous answers in this video series like this because in all of our previous answers the main product was neutral. If the main product was neutral, we probably would not even include this negative leaving group in the answer. But when our main product has a positive charge, the conventional way to write the answer is to show this negative leaving group close to the main product in a kind of ionic bond. Carbon-3 here is a stereocenter. It's attached to 4 different groups. Should we invert the configuration at carbon-3? No, because carbon-3 is not participating in the reaction. Carbon-3 is not the alpha carbon. So the configuration of carbon-3 should not change. If you changed carbon-5 from a wedge to a dash, that would be a mistake. Carbon-3 is not participating in the reaction. We would only invert the configuration for SN2 at the alpha carbon, and there's no need to do that for this problem because the alpha carbon for this problem is not a stereocenter. Carbon-4 is not a stereocenter because it's not attached to 4 different groups. It's attached, 2 of the groups attached to carbon-4 are 2 identical hidden hydrogens. So there's no configuration that we need to invert at carbon-4. Well, remember that our main goal for this video is to learn how to deal with neutral nucleophiles. The trickiest part of dealing with a neutral nucleophile is remembering to change the charge from neutral to positive. The most common mistake students make is forgetting to change this charge from neutral to positive, and therefore you would lose a lot of credit if you forgot to change that charge. make sure that you always remember to change 2 charges on each mechanism step, and watch out for this most common mistake. The most common mistake is forgetting to change the formal charge for the atom at the beginning of the string of arrows. You should always change 2 formal charges at the beginning and the end of the string of arrows, but unfortunately students often forget to change the formal charge for the atom at the beginning of the string of arrows. Please pause the video and try this problem. We can put in some numbers. It's difficult to number these carbons because there's 3 separate methyl groups here, and we probably won't make any mistakes with these, so I won't try to number these carbons in this particular case. We should look for ionic bonds. There are no metals in the starting materials, so there are no ionic bonds. In particular, you should know that phosphorus is a nonmetal. Carbon and hydrogen are nonmetals, so this compound is completely covalently bonded, which means that we can trust that there are no formal charges in this compound, since none were drawn for us. Now we identify the roles. Well, there are no negative formal charges to use as a nucleophile, but we've memorized that neutral phosphorus has a lone pair, and therefore we've memorized that neutral phosphorus can be used as a nucleophile. What about neutral chlorine? Could we use the neutral chlorine as a nucleophile? Well, neutral chlorine does have a lone pair, but we've memorized that neutral chlorine is not used as a nucleophile. Instead, neutral chlorine is a leaving group. So we expect the neutral chlorine to be a leaving group. Since the chlorine is attached to carbon 4, that'll give carbon 4 a delta positive charge, which will make carbon 4 electrophilic. Carbon 4 is also our alpha carbon because it's attached to the leaving group. Now we identify the mechanism. Don't just assume the reaction is SN2, let's figure it out. Carbon 4 is a secondary alpha carbon because it's attached to 2 carbon chains. Make sure you write down that it's secondary. So we're in the middle row. Our nucleophile is neutral phosphorus. Neutral phosphorus is here in our middle column. So the table predicts that we're here, an SN2 reaction. Write that down. Now we can draw the arrows. The arrows go from the nucleophile towards the alpha carbon, and from this bond to show the leaving group leaving. The nucleophile attacks the alpha carbon, and the leaving group leaves the alpha carbon simultaneously in the same step. Now we draw the products, being careful to number all the carbons. This arrow tells us to draw a bond. Between which 2 atoms? Between the phosphorus and carbon 4. Now, we know that the nucleophile has to attack from the side opposite to the leaving group. So since the leaving group started behind the page, the phosphorus has to attack from in front of the page, which means the phosphorus should end up on a wedge. Phosphorus ends up on a wedge. Should the phosphorus still be attached to these 3 methyl groups? Well, yes, because the methyl groups were covalently bonded to the phosphorus, and we would only break covalent bonds if there was an arrow telling us to break the covalent bonds, and there is no arrow telling us to break those covalent bonds. So it would be a big mistake to leave these 3 methyl groups out. Make sure you include all 3 methyl groups here in the product. Do you understand this notation? This condensed notation means that there are 3 separate methyl groups attached to this phosphorus. Let's see here. So what happens to this hydrogen? Well, the hydrogen started in front of the page, but the phosphorus attacked from in front of the page, which would push the hydrogen behind the page. The hydrogen has been pushed from in front of the page to behind the page, so we really have inverted the configuration at our alpha carbon. You don't have to draw this hydrogen. You could leave the hydrogen out completely and treat it as a hidden hydrogen. But if you do draw it, you have to draw it on a dash. If you drew the hydrogen in the product on a wedge, your product would be a mistake. And if you drew the hydrogen in the product on a solid line, that would also be a mistake. In order to correctly show a tetrahedral geometry around carbon 4, we have to have 2 solid bonds, a wedge, and a dash. Or we could, like I said, just leave the hydrogen out completely as a hidden hydrogen. Now, most important, because this is the first arrow, we need to change a charge. We need to make the atom that loses electrons from this arrow one step less negative. So the phosphorus started neutral, it's losing electrons, so it becomes one step less negative, or one step more positive, which means the phosphorus ends up with a positive formal charge. This positive formal charge is the most important part of the product to get right, and it's also the part that students are most likely to get wrong. Now this arrow tells us to break the bond between carbon 4 and the chlorine, which I've already done. Because the chlorine is at the end of the series of arrows, it should gain a negative charge. And remember that the conventional approach when your main product has a positive charge is to show it ionically bonded to the other product by drawing the two species close to each other. So I'll show the chloride close to this positive phosphorus to show an ionic bond between them. So this would be the most conventional way to draw the product for this problem. Remember, make sure you change two charges. The most common mistake would be forgetting to change the charge at the beginning of the string of arrows, forgetting to change the charge on this phosphorus. Now, I should mention that this type of product is actually pretty unusual in introductory Ochem. In introductory Ochem, we don't usually get a main product that has a formal charge. In introductory Ochem, we usually continue the mechanism until we can eliminate the formal charges in the main product. So this is actually fairly unusual in Ochem. So you should keep in mind this is fairly unusual. Usually in Ochem, we would keep doing steps in the mechanism until we could eliminate formal charges in the main product. But SN2 is an exception to that. If you do an SN2 reaction using a neutral nucleophile, we generally just accept that the final product of that SN2 will have a positive formal charge on the main product. So again, my point is that this type of answer is correct, but it's also unusual in Ochem. Most other reactions in Ochem would not be finished until we eliminated the formal charges on the main product. SN2 is an unusual reaction where if we do an SN2 with a neutral nucleophile, it's okay to have this positive formal charge on our final product. And in fact, it's required to have this positive charge. Without the positive charge, this answer would be wrong. When you study other reactions later in your Ochem class, you'll see that this is unusual and that most mechanisms for other reactions are not finished until we've eliminated the formal charges on the main product. Please pause the video and try this problem. Here's our solution. We'll start by numbering all the carbons. Notice that I numbered all the carbons in both starting materials. Now we should look for formal charges by looking for ionic bonds. But there are no metals, no sodium or potassium here, so there are no ionic bonds. In particular, everything in this compound is a nonmetal. You should know that sulfur, carbon, and hydrogen are all nonmetals. This is completely covalently bonded. So since no formal charges were drawn, we can assume there's no formal charges in these starting materials. Now we identify our roles. Normally we would look for a negative formal charge for our nucleophile, but since there is no negative formal charge, we look for a neutral nucleophile, and we've memorized that neutral sulfur. We've memorized that neutral sulfur has a lone pair. Actually, it has more than one lone pair. It has two lone pairs, but it has at least one lone pair, and therefore neutral sulfur is nucleophilic. We've memorized that neutral iodide is not nucleophilic, even though it has a lone pair. Instead, neutral iodide is a good leaving group. Carbon 4 has a delta positive because it's attached to the iodide. Carbon 4 is our alpha carbon. Because of the delta positive, carbon 4 is our electrophile. So now we can identify what type of mechanism we're using. We have a primary alpha carbon. Carbon 4 is primary. Put this in the top row of our table. Our nucleophile is neutral sulfur. Neutral sulfur is in our middle column. That puts us in this cell, so we expect an SN2 reaction. So The electrons go from the nucleophile towards the alpha carbon, and another arrow to show the leaving group leaving the alpha carbon. Now we can draw our products. This arrow tells us to draw a bond between which two atoms? Between carbon-4 and the sulfur. Should the sulfur still be bonded to carbon-6 and 7? Yes, because those are covalent bonds, so they don't break. One way you could write that would be, we could write that like this. Remember to keep numbering all the carbons. I hope it was obvious to you here that this sulfur was not bonded, obviously, to any of these three hydrogens. This sulfur is bonded to carbon-7 and to carbon-6. That's how to interpret this condensed notation. The three hydrogens are on carbon-6, not on the sulfur. So one way we could write this is like this. Now the most important part to get right is the charges, because this is the first arrow. This sulfur that's losing electrons should become one step less negative, one step more positive. The sulfur started neutral, it's losing electrons, it becomes one step less negative, one step more positive, which means the sulfur ends up with a positive formal charge. This positive formal charge is the most important part of the products to get right, and it's also the most common, forgetting the positive charge would be the most common student mistake. Let's see, this arrow tells us to break the bond between carbon-4 and the iodide. The iodide is gaining electrons from this arrow, so it becomes negative. And because our final product has a positive charge, the conventional answer would be to draw the iodide close to the positive sulfur to show an ionic bond. So I've drawn the iodide relatively close to the sulfur to show an ionic bond between those products. In this video, we learned how to handle SN2 reactions that involve neutral nucleophiles. We learned that the possible neutral nucleophiles are oxygen, nitrogen, sulfur, and phosphorus. We've learned that neutral nitrogen, phosphorus, and sulfur are good nucleophiles, so they can be used for SN2, whereas neutral oxygen is a poor nucleophile, which cannot do SN2. And we've seen that the most common mistake that students make with neutral nucleophiles is that students often forget to change the charge on the neutral nucleophile from neutral to positive. But that is not a minor detail. Getting the formal charge right is the most important part of drawing the product correctly. Time for a review quiz. From memory, see if you can draw the table for choosing between SN2, SN1, E2, and E1 reactions for alkyl halide and alkyl sulfonate electrophiles. Remember that the table is really the best, most reliable way to choose between these mechanisms, but you can't really use the table unless you have it memorized. No time like the present, please pause the video and see if you can draw the table from memory. Here's that table. You should check what you wrote down against this table. Be tough on yourself. Be tough on yourself and make sure that you got all the details correct. For example, this table isn't much good unless you know which nucleophiles go in which columns. So when you wrote out the table, I hope that you were careful to write which types of atoms went at the tops of which columns. Otherwise, you can't really use this table effectively. If you were able to write out this table from memory, great. If you were not able to write out the table from memory, now's a good time to memorize the table and try again. So I would suggest that you should keep trying to draw out this table from memory over and over right now on blank pieces of paper until you can succeed in drawing the table correctly from memory. Your success on the next midterm will probably be much helped if you have this table memorized. I'm assuming here that you're taking an Ochem class where you're not allowed to use notes. Obviously, if it's an open notes test, you could just have the table in your notes. But if you have to rely, if you're not allowed to use notes, you need to have this table memorized. And in that case, the sooner you memorize the table, the better.